In this lab, we will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, and this motion is similar to motion in extreme rope sports. This motion seems complicated, but using Newton's second law and the energy principle, we can understand and predict this motion. We also use Tracker to show the actual movement of the spring and VPython to make a computational model of this movement. From this modeling of the data, we find that VPython creates a model of the motion of the spring mass system that has a significant amount of deviation. We will go into possible causes for this later. On the other hand, it models the energy principle relatively well. In order to model the motion of extreme sports involving ropes, we must first take into account that real climbing ropes stretch by a significant amount during activity. At a microscopic level, we can see that the stretching of the rope is due to spring-like bonds, and we can think of all of these chains as one spring as we model the rope. However, to model the system, we will be looking at a mass on a spring rather than a climber on a rope for simplicity purposes. Using Tracker, I was able to analyze the motion of the spring mass system once it was released. When I play it, you can see that the system moves around in an ellipse, moving in both the x and y directions, and we can see on the graph in the top right corner the motion when we plot the x versus time, or the y versus time, and then the x versus time. In order to update the VPython code, there's a lot of information we need to gather. First, we are given that the mass of the object is 0.402 kilograms. We can extract the initial position data from Tracker, where time equals 0. For the weight force, we already have the mass, but we also need gravity, which is 9.8 meters per second squared. We also need to input the spring force, the stiffness K, and L naught, the relaxed length. First, we can solve for the stiffness of the spring. Before that, though, we need to know the period of oscillation. By using the graph from Tracker, I found this value to be 1.613 seconds. If we rearrange the equation for t, the period of oscillation, to solve for k, we get that k equals 4 pi squared times mass over t squared. When we plug in our values and calculate, the stiffness is found to be 6.099 newtons per meter. To find L naught, we use the equation L naught equals magnitude of L minus mass times gravity divided by the stiffness. So we plug in our values and get that L naught equals 0.054 meters. These values, as well as L hat, are mentioned here in the code. In addition, I had to edit the equations for the force of gravity, the spring force, the net force, Newton's second law, and the position formula into the code. These are the equations where I will make motion predictions. We must add the gravitational force, the spring force, and the net force, use Newton's second law to predict the new velocity, and then use that to predict the new position. Now we will take into account the energy principle. We will make the system now include the spring, the mass, and the earth. According to the energy principle, the change in the total system energy, delta E, equals the change in kinetic energy of the mass, delta K, plus the change in gravitational potential energy, delta U sub G, plus the change in spring potential energy, delta U sub S. Because the system includes the Earth, there are no interactions that transfer energy to the surroundings if we neglect small effects like air resistance. The attachment point of the spring doesn't have displacement, so there is no work done and no energy transfer. Because of this, the right side of the energy principle is equal to 0. To compute our energy changes in the model, we need to calculate delta K, delta U sub G, and delta U sub S at each iteration. We can put the equations for these three values into the code and find the initial energies. To compute the final energies, we can edit this part of the code to include the correct formulas. With all of these edits in the code, we can run it to show us graphically and in model form the motion of the spring mass system. Delta K is represented in the blue line, delta U sub S is in red, delta U sub G is in green, and the total system energy is yellow. We can see that delta K, delta U sub S, and delta U sub G all oscillate, and the change in the spring potential energy and change in gravitational potential energy have the same period. These changes in energies are also about the same size but opposite in phase, so when one increases, the other decreases, and vice versa. Looking at the blue line, the change in kinetic energy, we see that it alternates between being positive and negative, which means that the mass gains and loses kinetic energy as it moves. The yellow line is the sum of all these changes, and it is 0, which we predicted would be the case earlier because of the energy principle. Therefore, because the total energy is 0, the energy principle is satisfied. If we update and uncomment some of the lines in the code to include the data taken from Tracker, we can make another comparison model showing the actual motion of the spring mass versus the predicted motion. The red ball shows where the mass is observed to be, and the blue ball shows where the computer model predicts where the mass should be. The time between each observed position is 20 times longer than the time between each predicted position, which might explain why there is a significant deviation between the observed and predicted positions. On the graph, we can see the predicted position in blue and the observed position in red. You can see that instead of the lines being very similar as they would be if the predicted position was close to the actual position, they are very opposite to each other. One reason for this large deviation could be that the total change in energy probably isn't exactly 0. In all energy transfers, some energy is transferred to the surroundings in the form of heat. Another possible reason for the seemingly inverse deviation is a mistake in the coding. My estimation of oscillation period in the x component is 1.71 seconds, and for the y component 1.63 seconds. The fact that the periods are slightly different will not affect the model because some of the energy is dissipated out, and so there will not be constant energy. In conclusion, the plots modeled the energy principle well, but the computational model deviated from the actual model, likely because of energy going to the surroundings or because of a calculation error.